Hey guys, we're back with the second video in our 5.3 section. In our last video we talked all about conditional probability. In this video we're going to talk about what makes events independent. So let's start off with an example. If event A is flipping heads on a fair coin and event B is flipping tails, we want to know what is the probability of B given A. That is, what is the probability that I land on tails of a coin toss given that my previous toss landed in heads. And then we also want to know what is the probability of A given B. So again, what is the chance that I land on heads given that my last toss was tails. So for both of these, they end up being 1/2. And you may be thinking, Miss Miller, it doesn't matter that we know what the previous toss landed on. We don't need to know that because no matter what, it's always going to be the same probability. That is what independent is. When knowledge that one event has happened does not change the likelihood that another event will happen, we say that these two events are in fact independent. Okay? So here's our formal definition. Two events, A and B, are independent if the occurrence of one event has no effect on the chance that the other event will happen. So, events A and B are independent if the probability of A given B is just the probability of A, and the probability of B given A is just the probability of B. Now, it has to be both, not just one. So if you check one, if it works out, you got to check the other one and be sure that they both work out. Now, of course, if you've checked one conditional probability and it doesn't hold true, no need to check the other one because you have enough information to show that they are not independent. So we're going to go through a few examples just to make sure we understand this idea of independent. And you might be thinking that it should be obvious if you were to think about, oh, these two events don't have any effect on one another. There's no association there. You can't just go with what your thoughts are or what your gut is telling you. You have to have an actual calculation to prove independent. And this is going to be something that holds true for the rest of the year. From this two-way table, we collected data talking about your handedness, right? Whether you're right or left-handed, and then your gender. We want to know, are the events male and left-handed independent? Okay, so let's go through a conditional probability. The probability that you are left-handed, given that you're male, is 3 out of 23. So 3 left-handed males out of the 23 males, which is about 0.13. Now, the probability that you're just left-handed is 7 out of 50, which is about 0.14. Now, you'll notice 0.13 is not the same as 0.14. These probabilities are not equal. Therefore, the events male and left-handed are not independent. Even though it's really close, okay, they are not independent. Now, before we go into the next example, I want to talk about this for a second. If we were to gather this data from a much, much larger population, right, this only came from a sample of 50. These might in fact be equal, okay? Now, in later chapters, specifically next semester, we'll talk about, well, they're not the same, but they're close. Are they close enough to show that there is an association or there is not? In our next semester, we'll talk about how we can actually prove one way or another or come to a stronger conclusion. But at this point, all we can say is they are not independent. Similar two-way table, but different population, different sample size. We were looking at, again, gender versus handedness. We want to know, are the events female and right-handed independent? Now, you might notice that there's no totals here, so you should probably go ahead and add those in so you can figure out some of your probabilities. So, let's go through our first one. Probability that you're right-handed, given that you're a female. Well, there are 18 right-handed females out of a total of 21 females. So that's 18 out of 21, which is about 6/7. Now, the probability of just being right-handed is 18 and 6 is 24 out of 28, which also simplifies to 6/7. So far so good. It's looking like they are independent, but I do need to check the other way. The probability that you're female, given that you're right-handed, is 18 out of 24. So what's the probability that you're female? 21 out of 28, and those both simplify to 3/4. So since the two conditional probabilities are equal to their probabilities without the condition, then we can say that the events female and right-handed are in fact independent. You would need to show these calculations to prove it, right? All four of these calculations. And with the explanation that's written here. Just like in the last example where I said since the probabilities were not equal, we knew they were not independent. You have to spell it out. How about you try this one? Press pause. We have whether or not you're a junior or senior, and then earned an A in AP Stats versus earned an A in AP Calc. We want to know, are the events junior and AP Calc independent, and are the events being a senior and being getting an A in AP Stats independent? So press pause and try these out. For the first one, the conditional probability junior given AP Calc is 7/16, whereas the probability of just junior is 12 out of 33. Since these values are not equal, the events are not independent. Second example, the probability of senior given AP Stats is 12 out of 17, whereas the probability of just being a senior is 21 out of 33. Again, the values are not equal, so the events are not independent. This is a good way to show your work, to spell it out, and answer your question fully. Now, I do want to spend a couple minutes talking about the relationship between independence and mutual exclusivity. In our last section, in 5.2, we talked about what it means to be mutually exclusive. We used examples of Venn diagrams, not overlapping, right, saying there's no probability of A and B. Being mutually exclusive and being independent, they have no relationship to each other. So I just kind of want us to think about them in a few examples. Now, these next three all have to do with picking one card from a deck of cards, okay? So just remember, there's 52 cards in a deck, half red, half black, so on and so forth. For our first example, let's let A be the fact that it's a red card, B be the fact that it's a club, is the suit. Now, are the events mutually exclusive? And then are the events independent? So, is it mutually exclusive? Yes, you cannot pick a red club, right? Clubs always have to be black. If you pick a red card, it's either a heart or a diamond. Now, are the events independent? What's the chance you pick a red card? Well, half the cards are red. What's the chance, the probability that it's a red card, given the fact that you know you picked a club? So let's say I pulled out a card and said, hey, it's a club. What's the chance that it's also red? 0. It's not possible. Therefore, they're not independent. So these two events are mutually exclusive, but they're not independent. Okay? Let's look at another example. All right, pick another card. A is that it's red. B is that it's a 7. Are they mutually exclusive? Are they independent? No, they are not mutually exclusive, right? Because there are two red 7s, right? There's a red 7 of hearts and there's a 7 of diamonds. Now, are they independent? So you have to check. What's the chance it's a red card? A half. What's the chance that it's a red card given that I told you it's a 7? Well, there are 4 7s and 2 of them are red. So you have a 1/2 chance of it being red if you tell me it's 7. Those are the same. So now I check the other way. What's the chance I get a 7? 4 to 52. All right, which is the same as 1/13. Now, what's the chance I get a 7 given that you told me it's red? Well, there are 2 7s out of the 26 red cards. And so that also simplifies to 1/13. So in this case, they are, in fact, independent because all of those probabilities are the same. So in this case, they were not mutually exclusive, but they were independent. All right, last one. Probability that it's A is red, B is that it's a heart. Think for a moment. Are they mutually exclusive? Are they going to be independent? So they are not mutually exclusive because if you have a heart, it is going to be red. So there is overlap there. Are the events independent? So if I told you what's the probability of picking a red card, we know it's a half. The probability of it being red, given that you tell me that you have a heart in your hand, 1. I don't need to further find any other probabilities because these two are different, therefore they are not independent. So keep in mind that independence and being mutually exclusive are two completely different things. One does not really relate to the other. Okay, so try to keep that straight. In our next video, we're going to be looking at tree diagrams, how they're going to help us solve some problems, keep our probabilities straight. And then we're also going to learn about the general multiplication rule. In our last section, we learned about the addition rule, so now it's only fair that we learn about the multiplication rule.